So here we are, we've conducted a simple linear regression on our x and y data using the method of least squares from Gauss. And now we want to dig a little bit deeper into what we can actually say about this model here. So let's just assume our model looks like this: y equals beta naught plus beta 1 times x. And actually we want to give these regression variables here, regression parameters, a small hat, indicating that they're just estimates of the true parameters. And what do I mean by that? Well, we have to keep in mind that we're always dealing with a population here of x and y measurements, values, whatever. And if we could, we would measure all the x and y's, and then we could set up the correct linear relationship, if it exists, between x and y. So these parameters, beta naught and beta 1, would be computed using all possible available data from the population. Now that's almost never a possibility. So what we do is that we take a sample, and the sample is these data points here, x and y values, and then we compute from those values our best guess of a linear model, so that beta naught hat is an estimate of the true beta naught, that is the intercept with the y-axis, and beta 1 hat estimates the true beta 1, the slope. All right. The thing is, if we took another sample and did this all over again, we would get different results for beta naught and beta 1. And if we took another sample, we'd get yet different. So every time we did this, we would get different results for beta naught and beta 1. So that leaves us in kind of a bad place, because what can we even say about beta naught and beta 1? If we get different results every time that we do the experiment, what can we even say? I mean, this number that we got here and this number that we got here, they're just one out of many we could get if we did this procedure over and over again. So the thing is, they have a distribution. So let's just assume that we did this experiment, this sampling, over and over again, and every time we computed beta naught and beta 1 using the method of least squares. And let's just use beta 1 as an example. So we'd get a value here and 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 here, like that. And after we've done this 1,000 times, we kind of get a distribution with a mean, which is our best guess for the true beta 1. Right. The problem, the question now is, what is this mean? What does these sampling measurements indicate that the mean is? What is this value? And one way to approach this is to state a null hypothesis saying that the true beta 1 is equal to 0. Why is 0 interesting? Well, if beta 1 is 0, that means this line is horizontal. That means that there's no relationship, no dependence whatsoever between x and y. So that's kind of a critical value. We're interested in knowing, is there any significant difference? Significant relationship between x and y? Is there at all any linear relationship between x and y? So if we can reject this hypothesis, that would make us happy, I guess, because then we've shown that there is a significant linear relationship between x and y. And you might say, well, I have this line. I can see that beta 1 is negative. It's not 0. So why even ask this question? But just remember again, this is just one out of many possible samples that we could make. Next time we do this experiment, maybe we get a regression result which looks like this. And next time we do the experiment, we might get a regression result that looks like this. I don't know. That's a possibility. So, and the thing is, this slope that we computed here, is it mostly a result of random noise, or is the slope significantly different from 0? Not just different from 0 due to random noise, but because there is a linear relationship between x and y. That's what we want to know. And of course, we could ask the same question for the beta 0, beta naught. Is it significantly different from 0? That is, this slope up here, could it just be 0? The reason we got something different from 0, is that just randomness, or is it because there is a significant, it has a significant difference from 0? Those are the two hypotheses that we want to test. How do we do it? Well, as I'm kind of suggesting with my drawing here, testing beta 1, testing this hypothesis is like testing the mean of this distribution of beta 1s. So you wouldn't be surprised to find that the test statistic that we want to state is the current value of beta 1, the one that we actually found in our model, minus the hypothesized value of beta 1, we might call it 1, 0, divided by the standard deviation of beta 1. Now, if we could write a test statistic like that, this would have a z distribution, a standard normal distribution. And keep in mind, our hypothesized value is 0 in our case here, because that's what the null hypothesis claims. Problem is, we don't know the standard deviation of beta 1. So we have to estimate it. It turns out that we could compute the variance of beta 1 if we know the variance of the y values, the response values. We would just divide it by the sum squared deviation of the x values, and that would give us the variance in beta 1 here. But again, we don't know the true variance of the y values here, but we can estimate it. Using the variance in the residuals. So we estimate it using the mean sum squared error, it's called in the regression terminology. What is this number here? Well, that's basically, I'll change my color here. That's basically, if we draw these squares here, there's a tiny one there, there's one there. You know, we take the distance from the observations to the model prediction. Those distances we square, and then we get areas corresponding to these squares that I'm drawing here. I'm not drawing all of them. Taking the sum of these squares and finding the mean area of those. That's, roughly speaking, this number here, the mean squared error. So we call this the error, right? That's the error. And if you take the square of that and sum it up and find the mean, then you get the mean square error. That's our best estimate. That's an unbiased estimate for the true variance in the response variable here, in the response values. Right. So, since we don't know it, we have to estimate it. So if we replace this true variance by the estimated variance, that is this mean square error here, divided by the sum square error of the x values, then we get what you could call an estimate of the variance in beta 1. Now if we take the square root of that estimate, then we get what we call the standard error of beta 1. That's just another name for something we could call the standard deviation, but we use the term standard error. Standard error for beta 1. So that's the same as this number here. We should just show it that's this one, the variance estimate divided by the sum squared deviation for the x values, and we use the mean square error to estimate this one. So we get mean square error divided by the sum squared deviation. Now what is the sum squared deviation? Well, that's just to remind ourselves. That's just taking each x value and subtract the mean and square that and sum for all the observations here. That's what that means. Well, since we don't know the true variance here, but we're estimating it, well then you wouldn't be surprised to see that what we find now is something that has a t-distribution instead of a set distribution. So we'll call the test statistic, and I'll just write 0 because 0 is the hypothesized value here, divided by the standard error of beta 1. Now that is a test statistic which has a t-distribution with n minus 2 degrees of freedom. And the reason it's a t and not a z distribution is because we've estimated the standard deviation down here, the standard error. The reason it has n minus 2 degrees of freedom is because our variance estimate here, or error estimate here, is based on the residuals, right? It's based on the MSE number here, and that comes from the residuals. That comes from those distances here, all these distances. How can we compute these distances? Well, first we have to compute the model, the red line here, and the model basically consists of two numbers, the intercept and the slope. How do we find these numbers? Well, we use the data to compute those numbers. So we use up 2 degrees of freedom to compute those two numbers, slope and intercept. And that's why we have to subtract 2. Because finding this standard error here, we've already used the data twice. Therefore, it loses 2 degrees of freedom. All right, so that's the test statistic for this null hypothesis here. If we want to do it for the beta naught here, the intercept over here, it's the exact same procedure. The only difference is that instead of having this expression for the variance in beta 1, we have another one for beta naught. So the variance for beta naught is given by the variance in the y values times 1 over n plus the mean of the x sample squared divided by the sum squared deviation for the x value. Again, we don't know this one, so we estimate it by the mean square error, just like we did before. So altogether, that leads us to the standard error for beta naught is then the square root of the estimate of the variance, which is the MSE, times 1 over n plus x bar squared over the sum squared deviation in the x values. So for the beta naught, we have the same kind of test statistic, except we use beta naught here. And for the standard error, we use this expression down here instead. Like that, and like that. No, sorry, the standard error, that was this one. So we are going to be doing this in Excel, but that will be in another video. Before I finish this video, I just want to say we also want to compute confidence intervals. Let's say 95%, that's the typical confidence interval. Let's say for beta 1. And the way we do that is, well, that's kind of standard procedure. We take the actual sampled beta 1, the one we found in our model, and we add and subtract the t quantile. For, in this case, that would be 0.975. Again, n minus 2 degrees of freedom times the standard error for beta 1. And that gives us a confidence interval, a 95% confidence interval for the beta 1. So that gives us the value, the true value of beta 1, or in another way to put it, the true value of beta 1 is in this interval with 95% confidence.